Hello, everybody. Welcome once again to the FKA Academy. Today, we're going to talk once again about automated driving. As promised last week, we have now the second part of these 3 sessions on automated driving. Today, we're going to talk about technical aspects of automated driving. And we have a presentation by Mr. Sebastian Cloud, which is the team leader for function development of FKA. He's an expert on developing all kinds of different modules and functions for automated driving. And without further ado, I give the word to Sebastian, who will give you the talk today.
Yeah, thank you, Adrian, for the kind introduction. Welcome from my side as well. As Adrian said, today I want to show you some more technical details. I think last week you heard a lot of information, or like you got an overview about what all kind of different sides of automation means. So not only technical levels, but on the social level and the history and everything. So today I want to focus a little bit more on what we actually need for automated driving. So that would mean how would we classify different algorithms, what we use. And I think Adrian already showed you last week a model which we use to basically categorize our algorithms. So the alpha model with the different levels, starting on the skill level, going up rule-based, where we can learn, and the knowledge, where we basically apply knowledge we have, and that can actually be mapped to the development of algorithms or the classification of algorithms which we use for automated driving. One other aspect I want to mention here is not only the different levels with skills and rule, but even like if we talk about automated driving or automated vehicle guidance, we have different levels. So, for example, we have the longest levels with the stabilization, guidance, and navigation, where we focus on the horizon. So typically on stabilization, we talk about milliseconds in the optimization horizon. On the guidance level, it's more seconds we talk, and of course you all know that if we talk about navigation, that can go up to hours of optimization horizon. So it's really important to differentiate when we talk about algorithms in which domain we want to use them, since there are plenty of algorithms available, and it's really important to have the right set of algorithms for the right problem you need to solve. So that is basically the ideas of levels, and what I want to lead you through today basically starts with sensor detections. Of course, the vehicle needs to perceive its environment, and I'll show you some details or implementation results from data fusion. So what we do with the detected information of the perceived information, how we classify that and bring that into an environmental model, and if we have all this information, how we actually analyze our situation. And so that's basically the rising part of the alpha model. And then on the way down, actually what we do with all the information we gathered. So we want to derive an action plan, generate a behavior, and intended behavior for the vehicle, make sure that we can generate a trajectory or plan a trajectory actually fitting that behavior or representing that behavior, and then of course making sure that we can actually make the vehicle follow that planned behavior or that planned trajectory. So before I want to show you some software results or software algorithms as an example, I want to start by showing you what we need from the hardware side and how I want to do that. I think if you saw it on LinkedIn, you may have already seen the animation of our test vehicle we use for our road testing, which is retrofitted. So as you see, it's a standard production car, but we retrofitted it with sensors. But that's typically sensors you can find on production cars. For example, here in the front, we just saw the LiDAR sensor, which is used in the A8. We have different radar sensors, so we cover the whole 360 degrees by radar sensors. And of course, the third technology we are using for this is camera system. We have a stereo camera system here in the front, for example, and of course we want to look in the rear-facing traffic, so we do the same in the back and make sure that we don't miss somebody when we do a lane change, for example. So that is from the hardware stack you would find on a standard vehicle for ADAS functions. And then on the rooftop, we actually have some more sensors, and I think you probably all have seen these sensors on Google cars. They made them famous back in the days. So we have the LiDAR sensors on the roof and on the sides. Of course, we use some high precision localization system using GPS and GLONASS, for example. So that's basically the sensors we are using to actually perceive the environment and to actually make the vehicle go in the direction we want. We interface the vehicle by applying acceleration and deceleration commands and steering commands as well. And of course, since it's a test vehicle and not a production vehicle, the computational hardware is stored in the trunk, where we use we run the algorithms on specific hardware. For example, for real time, we use different hardware than for computational programs which are heavily to compute. That we use just PC hardware in this example. Okay, so that was basically the hardware. So you saw what typical sensors are used for automated driving, and what I now want to show you is basically what comes out of a sensor, what the sensor sees on a raw level, and what we can do with this information. And I want to start with the image sensor, basically cameras, and you all know that is a really important sensor, not only since Tesla is focusing highly on image processing techniques, but a lot of information can be retrieved from images. So to do that, neural networks are state of the art for actually segmenting images. And what I mean by segmentation or semantic segmentation is that, as you see it in the video, we look at the image and classify the pixels by their type they're representing. For example, in the video, we see the vehicles are represented in blue, and the drivable space is purple, kind of purplish, and pedestrian walks are like a pink, and so on. So we have different classes to actually segment the image really good. And the way we're doing it is, of course, data. So we need a lot of data to actually train the networks quite well, and to make sure you can of course start with publicly available data sets. There are a lot of data sets available from the past. There is a Kitty data set, and we have seen a lot of new data sets, especially for automated driving, like the Waymo data set. So that's what's basically available, and what these data sets include is basically the images or the sensor data and the annotation. So you basically use the annotations to actually train the networks. And But to further improve all these detection technologies, you can apply different variation techniques. For example, you can modify the image by just flipping it and changing the brightness, the contrast, etc. So you still have the ground truth from the labels, but you make the network more robust against different inputs, different lighting situations, etc. You can actually go further and use GANs, where you actually apply textures to simulated images. There it's easier for you because the ground truth is available from simulation. So there are a lot of techniques which can be used to train the networks, and I think that is state of the art for image processing to derive the segmentic labels from the image. And what you can do once you have this, for example, you can do similar things with point clouds which are coming from the LiDAR. As you see, we have the LiDARs on the roof typically, and that's the point cloud we see in the image or in the video stream. And what we can do there is, of course, we try to do the same with as with the camera. But the good thing is that the LiDAR gives us the depth information because it delivers the distance to the points or the reflections to the obstacles. But of course, if you compare the image and the point cloud above, you see it's way more coarse than the actual image. So we don't have that much information available. But what we can do basically to derive the same information, like the labels and the semantic information there, we can cross-model train the data, so we can map the camera information onto the LiDAR point cloud we see, so we know where they are mounted on the vehicle. So we can actually cross-reference it and apply the labels from the camera to the point cloud. So that is a really good way to actually use or like segment point clouds at this point. And if we once have the segmented image, so or the image or the and the point cloud, we can go into the next steps and actually derive data which we can use for developing a driving function. So it's nice to have an image which is segmented with a lot of colors, but of course the information of that image is still not you can't process that in a way that you can use it in an ADAS or an AD function. So what we then do is basically we use the segmented point cloud and derive objects from it. So we do that by generating bounding boxes, and as you can see in the image, if you compare the video stream to the point cloud, you see the point cloud in white, and the red are the bounding boxes we put above all the objects, and you see the bounding boxes are actually following the object. So that's the first step to actually generate information we can use in the driving function there. So there are some more techniques where we can generate even more training data to do that, but it's the same with the image. As I said, we need a lot of training data to actually make it good to fit the network quite well to our data and our use case. So the same thing we can actually do with radar data. So as I said in the beginning, our vehicle is equipped with radar sensors all around the vehicle. So the good thing is the radars, for example, they see through fog and everything compared to a LiDAR or camera. So it's really good to have a redundant sensor setup, and it's really important to use all the different sensor technologies to fuse them. So for example, for the radar, in this video we did actually the same. We applied this time the LiDAR data, the labels from the LiDAR data, or we used the LiDAR data, the bounding boxes, as a label for our training for the radar data. So that's the way where we can then derive objects from the radar. So we have the two sensor systems deriving data, looking from different perspective at the scene, since they're mounted at different height and everything. So you maybe just saw in the video that for radar, sometimes even if they're mounted correctly, they can even see, I would say, through the lead vehicle, because they're bouncing on the ground, and see the vehicle in front of it. So that is actually a pretty good feature of the radar compared to the LiDAR. Just to give one example why it makes sense to use different sensors, because they all have different specs and different advantages and disadvantages, of course. So once we derived all the information from different sensors, so what I just showed you is basically looking image by image, point cloud by point cloud, looking at the data received from the sensor and saying, okay, here we see a car, here we see a pedestrian, etc. What we actually then do in the next steps, we try to match and track all the objects. Since we are driving around, so we have a time sequence, we know what happened in the past, so we can predict what will at least be in the next few steps. So for example, we try to track the objects, and we saw a car in the last frame, then we make sure that it should be there in the next frame. That's the same what a human would do. I mean, he knows we've seen a car there, maybe it's in the blind spot, some sensor can't see it, but it would still be there. And so that's just where tracking is really important for a stable object surrounding. And as I said, we have different sensors now. For the function itself, it wants to have one environment it can rely on. So what we do then, we basically use data fusion algorithms to bring all the information together. For example, here we derive the bounding boxes to actually have one single source of information with all the, for example, moving objects around us. So that's where we typically can apply Kalman filters or even particle filters to do that job quite well. So that's basically from the side where we can, what we need to do to actually perceive the environment quite well. And the next step is actually to generate an environment to relate all these information. So what I just showed you, that we are now able to say it's a car, it's a pedestrian. So we are able to classify objects in a way, but we need to bring it into a context, right? So what we drive, when we drive on the streets, we try to do the same. So we to bring it into a context. So we describe or we set up an environment model where we have some specific description on how our environment can be modeled, and then we do a situation analysis where we can actually derive some information what is currently happening around us with all the context gathered there. So an environmental model, you can think of two ways to do it. I mean, maybe more, but or hybrid approaches. But the first one is a really generalized approach. You can, for example, think of occupancy grid maps. So what occupancy grid maps do is they just look at a single location around you, or in your world coordinates or wherever, and say, I think there is this cell. You normally discretize it with cells. This cell is occupied with a specific distribution, or you are sure by 80% that in this cell you have an occupation. At this point, you do not classify what the occupation looks like. Is it a zone? Is it a parked car, or whatever? So that makes it really easy for you, for example, in less structured environment, for example, parking lots or off-road driving, for example, to just say, okay, that is something we don't want to hit, just go around it, but it doesn't allow you a lot of context info, or doesn't give you a lot of context information of this. For example, another way, even especially if you think of automated driving in structured environment like roads, for example, on highways or even urban areas, you have a really structured environment with normally lanes, separate bicycle lanes, pedestrian walks, intersections, etc. So what you can come up with some other representation, for example, a graph where you can gather all the informations. And this graph can typically be derived from a high definition map, where you can then use to map all the information, all the objects on it, and yeah, you can just simply derive information of the context. For example, this route has the right of way compared to the other route, so it gives you a lot of context, the environmental model. And this all this context is really necessary if we do one of the hardest part, I would say, the prediction. I mean, that's the same challenge for humans as well. We need to predict what other traffic participants do. We sometimes have help, for example, from traffic light infrastructure, controlling the right of way situation, but sometimes we just yeah, like we have some knowledge back in our brain telling us, okay, he will probably do this and that. So that's the same we do with the system. The system, of course, needs to predict what the traffic participant, for example, will do in the next seconds. And for example, the way you can do it with just some naive Bayes classification, matching the objects, as I said, to the road graph or the environmental model. And then for each object, you derive a road graph, and you see that on the video on the left, where we see the different options for each vehicle. It can either go straight, make a left, make a right, and then the probability distribution depends on the next actions of the vehicle, and they change. And at a certain point, the system is quite sure that we're making a right turn. Even still, there would be the possibility to make a U-turn in the last second. That's actually not listed here as an example because it's really unlikely to happen here, but it could, of course, happen here. So that is really all the information we gather from our surroundings. We do the predictions, and once we have anticipated the situation around us, we try to plan a maneuver to generate an intended behavior, and then on a higher level generate the behavior. What should the car do in the next seconds? And from this, how we can actually derive a trajectory the vehicle is able to follow, fulfilling all that generated actions there. So from decision making is then the next level. So what we do, we try to of course derive an optimal but high level driving decision from all the information we gathered. In this case, we can do that by using a partially observable Markov decision process, for example. It's some way of stochastic control process, and what you do the same way you do it with prediction and everything. You have discrete time steps, and the really nice thing about that partially observable Markov addition is that you can integrate the uncertainties of the perception system into this. And what it does actually in the end, based on all the uncertainties you've gathered over your process chain, it will generate a discrete set of actions which we want to execute. So it will basically generate a velocity profile. For example, here we want to give the pedestrian the right of way at a right turn. So you see in green the route it's supposed to follow, but you'll see that it really slowly is entering the intersection because of the pedestrian blocking its way, and now since the pedestrians cross the situation or the lane, it is able to make the right turn and decides to go. That is of course only a high level action plan, so it's basically saying stop here or change the position of the lane a meter to the left or something. So it's a really coarse information. So that's nothing we can feed into the control system. As an intermediate step, we need some trajectory planning happening in between. So what we did in the past step is to derive the high level plan to do it. So we already, on the highest level of decision making, we have already tried to decide on the optimal route or like optimal action plan, and then we can locally optimize the action set and derive a trajectory based on the inputs from the driving decision and of course all the informations here. So for example, what you saw in this example is that the decision making said we have the right of way, and it started driving because we had a green light. But then we have the car, you see it on the left, approaching and ignoring its right of way, so cutting us out there. And so we actually stopped there as well. So we still have some information about the environment on that level as well, ensuring that we always have a safe trajectory which we can execute without hitting anyone. So that is the different level of optimization. And as I said in the beginning, it's really important to always use the right set of tools for your problem. So it's a really good example where you need different planning levels or levels of planning detail to fulfill the whole driving task here. So for example, on the decision making, we just use a point cloud mass model, while here we go for a more sophisticated kinematic single track model, which we use to actually plan a drivable trajectory and making a comfortable driving experience for the users. The last way, basically coming more in the direction to the interfaces to the vehicle, is of course making sure that we are able to execute the planned trajectory. So for this, we typically add another controller which actually tracks the planned trajectory there, and it generates the specific lateral and longitudinal control commands which are then forwarded to the vehicle. So they can vary depending on the vehicle type you use, the degrees of freedom your vehicle model system gives you. For example, could be that you have a four-wheel steer system, so you can steer all four vehicles independently. Then we of course need to generate different lateral and longitudinal commands than for just a single standard vehicle with front axle steering. But the main job for the trajectory following controller is actually to compensate all the inaccuracy we had on the system model level. For example, as I said, the behavior generation just used a point cloud mass model. Then on trajectory planning, we use already a kinematic steering model, but that's way too not already perfectly detailed. So we will have always system inaccuracies there. So the controller is used to track the trajectory and compensate all this inaccuracy, and maybe even disturbances from outside the vehicle, like a slope in the road which was not probably detected by the system, which we need to compensate there as well. So then you saw it just on the left side showing our test vehicle going around our test track. For this vehicle, we technically use the standard ACC and steering interfaces from the ADAS functions, but of course it's a prototype vehicle. So if you want to put it in production, you need way more redundant actuation systems, and of course, as you see it in the video here, for our testing and all the testing which is currently going on in the world, you need some backup plan. And the backup plan for us always in this case, and if you drive a public roads, that's a good idea to have a safety driver on board, always monitoring the system behavior and making sure that you can test on the road safely. All the algorithms you maybe tested already in simulation, but now need to be verified in real-world traffic. Okay, so that's basically it from my side. I hope I was able to give you an overview about the concepts of automated driving function development and the technical aspects on this. Yeah, thank you very much for listening.